Hello and good day everyone, my name is Ron and let us answer some sensitivity analysis problems. Ethylene is produced from the cracking of ethane. Determine the plug flow reactor volume and length necessary to produce approximately 45,360 metric tons of ethylene a year from cracking a feed stream of pure ethane. The reaction is irreversible and elementary. Assume an 80% conversion of ethane and operate the reactor isothermally at 1100 Kelvin at a pressure of 6 atmospherics. Note that this can be a trial and error process. Other information's reaction rate constant at 1000 Kelvin is 0.072 per second, and the energy constant is 82 kilocalories per mole or 82,000 calories per mole. So this is our given value, and we are required again to find the reactor plug flow reactor volume and length necessary to produce 45,260 metric tons of ethylene a year. So we're given this diagram. I made it myself, and since ethane is a gas, it cracks to produce ethylene, which is also a gas, and hydrogen gas. Well, again, by the namesake, it's also a gas. So this means that we're dealing with gas phase reactions. Hence, in our hand calculation, we will do a gas phase algorithm. So this is the PFR and its corresponding details, and this is the chemical reaction. So this is ethane, it cracks, it yields ethylene and hydrogen gas. So we record what's the PFR volume or what's the PFR length. So before I start with the simulation, I would start first with the calculation in terms of the CRE algorithm. So if you've seen my previous video, you would know that the CRE algorithm is an algorithm created by the book of Fogler, The Elements of Chemical Reaction Engineering. And I use this algorithm in order to solve for my corresponding reaction engineering problems. So to start, this is the diagram of a plug flow reactor with its corresponding assumptions, steady state process, well mix, and volume changes for each component. And then the material balance, and I applied the assumptions earlier, then isolate this formula for PFR. Then the rate law, I used the power law model, and I defined it as follows. And since our given K is with regards to 1000 Kelvin, but our operating temperature is 1100 Kelvin, I would need to convert that using ratio and proportion using the Arrhenius equation. So this is the equation to convert the 1000 Kelvin K into 1100 Kelvin K to be used for the rate law constant. And the stoichiometry for gas phase. So since we're dealing with gas phase and isothermal, this equation would stay the same. However, this one would be equal to 1 since again it is isothermal. And doing a feed rate, doing the following procedures: feed rate to reactor. So this is ethane, this is ethylene, and this is hydrogen gas, A, B, and C respectively. Ethane is the only reactant, so it's negative. B is positive, C is positive since they are products, and subtracting them together to get the effluent rate, and dividing it by the final volumetric flow rate to get the concentration. And note that the final volumetric flow rate has this formula. We have these final equations. So I need to find, since we're dealing with gas phase reaction, we need to find epsilon. In order to find epsilon, we need to find del. Del can be calculated by summating all coefficients in this part. So we need to find first epsilon, del. After finding del, we need to find epsilon now. And then epsilon simply equals to the mole fraction of the reactant times del. Since the only reactant considered is ethane, this means that the mole fraction of ethane is equal to 1, since again, this is pure ethane. And the del is -1 plus 1 plus 1. So this is 1 times 1, so epsilon equals 1. And then we need to find the initial molar flow rate using this formula. So the initial molar flow rate, the initial molar flow rate of A. We're not given the molar. So if we're going to simulate this in DWSim, we're not given inlet stream details. We're only given product stream details. However, DWSim is a simulator that goes to forward calculation. So in order to do that, I need to calculate manually the molar flow rate of the ethane. So how do I do that? Using the stoichiometric table given below. So given in front, sorry. So since I already derived an equation of the final volumetric, final molar flow rate of ethylene, and I substitute the values as follows. So this is the value, and noting that there is no ethylene existing in the feed, since again we just need to use, the reaction is there to produce it. So this essentially equates to 0. Then we're left with this. We're already given a final value of the ethylene, which is 45,360 tons per year. We convert it into kilomoles per second using the respective conversions. So we have calendar year conversion to day to hour conversion to hour to second conversion, and then kilogram to ton conversion, and we'll convert it using 2 kilomoles using its molar mass of ethylene. Doing so, I would calculate that the molar flow rate of ethane inlet is equal to 0.0581 kilomoles per second. And then I combine everything that I know and derived earlier. So this is from the step 1, and this definition is from the stoichiometric table, so on and so forth, substituting and integrating with respect to V and X. I would find this formula, and I calculated that my volume should be 0.6897 cubic meter. So there is a statement here that the hand calculation does not match the simulator, and it is true. And I'll show you. I'll show you the weird thing about this hand calculation. So the process model shows. So we'll do the process model using the following algorithm that I've been repeating for the past few videos. So the general procedure, introduction, the compounds are, going back to the diagram, ethane, ethylene, and hydrogen gas. Property package, we'll use Raoult's law. Okay, we'll just use Raoult's law here to simplify operations. And then we'll use system of units is for our temperature, we'll put here Kelvin. Pressure, we'll put here ATM, atmospheres. Molar flow rate, we'll put here kilomoles per second, since that was what we calculated earlier. For mass flow rate, we would put here tons per year. We will put here kilogram per second. And volumetric flow rate, we'll also put here cubic meters per second. And then that's it. Pressure difference, we'll put here also as ATM, and we're finished. And then we need to specify the reaction. So going to reactions, and we need to say that this is the main reaction. Rename it as main reaction, and we need to add a chemical reaction in this folder. So we'll add here kinetic reactions. We're given kinetic data. We will include all components, and the base component is always the limiting reactant, and the limiting reactant, or just the reactant, essentially, since there's only one reactant, is the ethane. So since there's only one reactant, this is -1. The reason why it's 1 again, it's because according to the problem, there's no coefficient here. That's why we'll put here as 1, and we'll put here as +1. They correspond as products, and we will assume that it is a first order reaction due to the power law model having this form, which is also similar to a first order rate law equation. And you will note that if the stoic coefficient you've been inputting here is correct, if the stoichiometry represents as okay. This means that the amount of carbon, hydrogen at the left side is equal to the amount of carbon and hydrogen at the right side. So base component ethane, the basis is molar concentration, and it is a vapor phase. And then the minimum temperature is the temperature at which the reference temperature of K is at 1000 Kelvin. So put here 1000, and it is still, our operating temperature is between the range between 1000 and 2000, since our operating temperature is 1100, and this is correct, vapor. Arrhenius equation, so we're given an Arrhenius equation of 0.072 for A or K, and then the reaction rate, energy constant, is 82,000 calories per mole. So 82,000 calories per mole. And we'll click, before that, amount of units, kilomoles per cubic meter and kilomoles per cubic meter per second. and we'll click OK. We'll go back to the simulator, click this exit, and then we'll go to reactors, PFR. And then we'll rename this as PFR. Oops, sorry, add an additional P. And then we'll rename this as feed. And we will name this as product. And this is duty. Alright, so let's specify. So though we're not given inlet conditions, I was able to calculate an inlet condition myself using the stoichiometric table, where my molar flow rate of ethane is 0.051 kilomoles per second, 0.0581 kilomoles per second, and we'll just put here as basic temperature. And for the pressure, not really basic temperature. We're already given the temperature. Sorry. Since isothermally 1100, that means that the temperature inlet and out is equal to 1100. So put here as 1100 Kelvin and operates at a 6 atm temperature. So at least we have a inlet temperature to be specified, which is 6 atmospheres, and that is so. And the compound amounts, ethane is the only one in the feed, pure ethane, so we'll put here as 1 and the rest as 0. Accept, double check your values, and you are ready to go. We'll now go to the PFR. We defined that the process is isothermic in nature, isothermally, and then the main reaction is the reaction we specified earlier, and the dimensions are what we want to find: reactor volume, tube length. And so if that's the case, how do we do this? Doing a trial and error will be very, very tedious if you just keep repeating values, inputting and repeating values over and over again. That's why it's a good thing that DWSim has its own logical block that allows that will do the trial and error for us. So we'll go here to logical blocks, click controller block, and we'll input here as volume adjustment. So what we will manipulate the PFR value of volume, and what we want to have is a conversion of ethane to reach 80%, and we'll converge to flowsheet solver, and we will let the set tolerance be as is. Afterwards, PFR volume. So this is what we will change always, and this is our objective, to reach 80% conversion. Click OK. And before we start the reaction, we need to change the dimensions. So we need to change this into 1 meter and 1 cubic meter. So when we solve it, it cannot, because since there is 6 atmospheres that is being fed inside and such a small PFR, it is unrealistic. So we need to increase some values a bit. So let's increase it to 1 e to the 10, and this is also 1 e to the 10, and then input both 1 e to the 10, and then we solve it. It is still too high, so we need to adjust it a bit. Wait, let me delete this first. We need to first try to let this flow for a while. So we'll put here 16, and our flow sheet is calculated successfully. Now it is calculated successfully, and our conversion is around 3%. So such a large volume and large tube length, and still the same. Controller block, volume adjustment, manipulate PFR volume and PFR ethane conversion, converge 80%. We want 80%, and then afterwards we'll just solve it and let it iterate. So as you can see, the duty is changing for every iteration, and it keeps on increasing and increasing and increasing until we get our specified a conversion of 80% ethane. After finishing the respective iterations, it calculated that in order to reach 80% ethane conversion, a volume must be around 5.8 times 10 to the 17. That's around trillions or millions, I think. That's very, very large, and it is actually quite surprising that the reactor has this volume given, where I calculated from my hand calculation that my volume would be 0.69897. I don't need to do a percent difference to know that that difference is very, very large, comparing 1 to 1 times 10 to the 17. So that's why there is this description, the hand calculation does not match the simulator. So how do we prove that the simulator makes sense now? Well, we can approach it on another way. So there must be a reason on why the simulator yielded this value. Maybe it's because the property package of Raoult's law had a specific component that made it calculate this way, or maybe it's because through the ability of present process engineers that had this type of that has actually made this volume quite true, due to the fact that noting the product flow rate is 45,000 tons a year. So it is actually quite a lot. So regardless, though our hand calculation does not prove simulator's sense, let's prove it at another way. So we'll do a alternative solution. So we know, so I want to take reference to the book of Peters, Timmerhouse, and West, entitled Plant Design and Economics for Chemical Engineers edition. They stated some heuristics or rules of thumb with regards to reactor vessels respectively. The reason why reactor vessels is because the PFR container is a vessel itself, and sometimes vessels can be treated as drums or etc. since they just contain the liquid. The reaction is in another part, but essentially the vessel is a vessel itself. So for reactor vessels or vessel drums, they stated that optimum length diameter ratio for drums is 3, but a range of 2.5 to 5 is common. So, since we're already given the reactor volume and we cannot change that anymore since that's what the simulator gave us, to make sense of our final answer, since we're already given the volume and we need to find its corresponding tube length, we need to calculate the length that corresponds to a length diameter ratio of 3. So we assume, so how do we do that? We assume that what I also observed is that the PFR length has a very small effect on the overall conversion to the PFR volume. I'll show you. So what happens if I put here 9? So it's still 80. So let me delete the, no, actually I don't need to delete. 9, it's still 80. So what happens if I put 14? Now that's too high. What happens? It won't run. What happens if I put 7? 17, it is also too high. If I put here 7, conversion is 80. If I put here 4, conversion is also 80. So that means that the tube length has a very, very minimal effect with regards to the conversion of ethane. That's why, in order to satisfy the heuristic stated above, the length shall be changed accordingly. So rather than doing a trial and error solution to find out the ideal length diameter ratio, we can do it, rather than using a logical block, we can do it mathematically. So in order to find the diameter of a PFR, we can assume a cylindrical shape. The PFR is a cylinder. So the volume of a cylinder is always equal to pi r squared h, where r is equal to diameter divided by 2. So d over 2 squared times length, since height can be also equated to length when in terms of orientation. So we're already given the volume, which is this value, and we're already given the diameter. We want the diameter. So doing a algebra, I would isolate the form of diameter would be this equation. Then in order to find the length diameter ratio, I would just divide L over D. L is just L, and over D D has this formula, so I substituted it here. And then what I did now is that since according to heuristics, the optimum length diameter ratio is 3, my L over Ds would be 3, and L over square root of 4 times my V, which is 5.8869 times 10 to the 17 over pi L. Isolating it, I would calculate that my L, the length that would require to satisfy the heuristics or the rules of thumb, would reach a length of 1.8895 times 10 to the 6 meters. Very, very large as well. So my final answer is this one. This is a value gained from the simulator, which is V. And the length is with regards to my hand calculation that corresponds to the heuristics from the book of Peter Stimmerhaus and West. So what's my overall conclusion? The hand calculation was not able to match the simulator in any way, as you can see from 1 cubic meter to 1 times 10 to the 17th cubic meter. This may be due to the simplified approach algorithm from Fogler's book may bring compared to the complex iterative solution DWSIM does. Again, the hand calculation I did is all with respect to Fogler's algorithm, which is a very, very simplified and easy to follow method when understanding chemical reaction engineering. But in terms of simulations and actual scenarios, some iterative solutions and some complex equations may be needed. Hence why the DWSIM has far greater computing power compared to my simplified CRE algorithm that I showed you earlier. Additionally, though, such large values of PFR dimension may be expected due to the large amounts of product to be produced. Heuristics from the book of Timmerhaus also states that such large dimensions of reactor vessels are usually divided into smaller vessels that sum up to the total calculated volume in configuring it to either parallel or series connections. Taking note that this value may be unrealistic, but let's take into account that we're talking about 45,000 tons per year of ethylene. A single PFR to incorporate it would be very, very large to accommodate that specific weight. That's why some chemical engineers use this value from simulators, but rather than making a big vessel, they make smaller vessels and connect them respectively that totals the total volume into the volume given by the simulator. It might be hard to understand. Here's a visual diagram. So this is a representation of what the simulator shows us. So for example, this is me, this is my height, and this is the volume, the volume, the length. This is the volume what the simulator shows us. This is the 5 times 8 something to the power of 17. Very, very large. This is what the calculation shows, or simulator. This is what the simulator shows. However, in reality, though the simulator may give this total volume, it will actually be done in real life like this. So it will still follow the total volume such that it will be divided evenly into equal volumes of containers or vessels, so that it will be more manageable and it will be more economic. Because trying to construct this, all in all, would require large amounts of materials, large amount of space, and it would topple down very, very easily due to its very, very large height. The more higher a structure is, the more its tendency it could fall. And it is very, very dangerous and unsafe. That's why chemical engineers use smaller vessels, but multiple ones that are manageable in size and shape. It will not bring harm or danger to any of the operators nearby or communities for that matter. And it will be more economical in terms of materials. So, this is the same scale of the person. But in reality, compared to having, again, building a big, very, very large container, it will just be divided into equal small containers and connected it as follows. It can be a series configuration, where one container is connected to the other, and so on and so forth. It could be a parallel configuration, where one feed stream is divided into respective containers, and each of it will be combined back for the product line. Or it could also be a series parallel configuration, where the feed stream will be divided, and it will be series, and it will be recombined again at the end. And this is more manageable since it is in a manageable container in terms of a scale of a person. So this is my conclusion on the reasoning behind the values of the simulator and how would it be applied in real life. So again, my name is Ron. Thank you all for listening, and I'll talk to you all later.